The sky is a dome, no matter the shape of the earth. So people often say you can't tell the shape of the ground we're standing on by the shape of the sky. And the analogy they use is that you can't tell the shape of the floor by the shape of the ceiling. So here we have a planetarium on the left with a flat floor and a domed ceiling. On the right, we have a sloping floor and a domed ceiling. Here's an IMAX theater with a sloping floor and a flat ceiling. On the left is a sloping ceiling and a flat floor. On the right, we have sort of an organic house with a very irregular floor and an irregular ceiling. And lastly, we have a couple examples of vaulted ceilings. So it is true, you can't tell the shape of the floor by the shape of the ceiling. This is absolutely true. So here's another question. Can you tell depth with distance? So here's the Kelowna Theater in California, and we have the depth of the stage. It really doesn't look very deep. From the front of the stage to where that screen is in the back, it really doesn't look very deep. But in fact, it's actually 47 feet deep. You could play a full NBA half-court basketball game on the stage. It really does not look like it's 47 feet deep. Here's an example from Major League Baseball. The pitcher and the batter, they look like they're almost the same height. The pitcher looks like he's maybe 6 inches taller than the batter, even though they're both almost exactly the same height. But they're actually standing 60 feet apart. And that's because with distance, you get this thing called compression effect. You really cannot tell depth with distance. And a classic example of this is a Hollywood fight choreography, where obviously you don't want to punch somebody in the face if you're shooting a movie. But on the image on the left, I mean, that totally looks like that guy smashed him in the face. But in actuality, he missed. So here's a side view, and this is very cartoony from the movie Captain America, where Captain America is fake punching a fake Hitler, and they do it. He misses him by a mile. But that's kind of what the side view would look like. Instead of the head-on view where it looks like the punch might connect. So again, you can't tell depth with distance. Here's an example from one of my specialties, pyrotechnicians. Pyrotechnics is what I'm trying to say. So we have a stadium where they've got what they call proximate pyro, the little fountains in the front. And then we have shells, chrysanthemum shells in the back. And those shells are actually launched from mortars that are behind the stadium. But the human eye, I mean, those things would be layered in the sky, and you really wouldn't be able to tell the depth that much. And here's an example of setting up a fireworks field. And the mortars in the very, very far back of this and versus the mortars in the very front, the audience, from their perspective, when they see those shells going off, they're all going to look like they're being launched from the same tubes. And here's a classic example with the moon, especially if the moon's on the horizon. The moon may look like it is just coming up right behind that lighthouse. You really, like if you were to say, how far is that lighthouse? Well, how far is the moon? They both look like the same distance away. Same thing with the jet plane and the moon. They look like they're literally the same distance from the viewer. All right. So the question is, can you tell depth with distance? And the answer is no. Next, we're going to talk about forming images. How are images formed? So in the ancient days of illustration and artwork, things were very symbolic. People took artistic liberties. So, for example, we have the Egyptian goddess Nuit. She formed the vault of the sky or the firmament, so she's covered with stars. And then if you look at her arms, you're like, does she have two elbows? Like where's her shoulder? Where's her elbows? And it's like it wasn't, anatomically correct. And then, of course, there's cave paintings, which are, tens of thousands of years old. And we have some stick figures going on there. And so that was before they learned how to, represent things more accurately. So during the Renaissance, they came up with an artist's screen. So the artist would have a sort of a wooden spear or like a knife edge, and you put your eye up against this point, and you look at the screen, and you could very, very accurately draw a picture based on this grid, based on the lines, almost like the rays coming out from that point. Now, when I first saw this illustration, I was like, well, it's a shame they didn't show us what this artist was actually drawing. And then I found another version of this, and it turns out he's drawing a half-naked lady, naturally. Now, there's a modern version of this, which just uses a clear plastic screen with some lines etched in it. And so again, the artist looks through this, and then they can make an accurate representation. So the computer version of this is called ray tracing. So with ray tracing, there is no camera, there is no eye. You've got just geometry, just pure geometry. So you have a place where you want to place the camera, the virtual camera, and then you have a screen. So for this example, it's a very crude example. We have an image that's literally going to be 5 by 7 pixels in size. A very, very, very tiny image. And so you've got rays that are hitting the sphere, and you got rays that are missing the sphere. And so, every time you hit the sphere, you just draw a green pixel. And now that doesn't look very much like a sphere. So if we increase the resolution, if we just double the resolution to 10 by 14, again, that's very, very crude, but we start getting a little bit more of a circular image. And if we increase the resolution to thousands of pixels, eventually you're going to get a near photorealistic version of that same sphere, and all just using ray tracing. And some of the early computer animations used primitive versions of ray tracing. These are two of the early Pixar shorts, Luxo Jr. and Tin Toy. And they specialized in making models made out of primitives. So there were spheres, there were cylinders, there were cones, there were flat planes, things that could be represented very easily in the mind of the computer. But now things can get really quite complicated. You have scenes with multiple objects, multiple light sources, and even reflective surfaces. So here's a beautiful image, all done in the mind of the computer. So those objects don't actually exist. That was all done with ray tracing. So the question is, or the statement is, images can be composed and rendered without the human eye. So all you need is the rules of geometry and linear perspective to get it done. So do you need the human eye to form images? And the answer is no. Next, we're going to discuss angle of view. So let's say you're at the bottom of a well and looking up at the sky. The sky may look like just like a circle or maybe a circular screen. You really don't get very much of an angular view. So if you see the diagram on the right, there's a little man and he's stuck at the bottom of a well. He only sees a couple degrees angle of view. But now we have a prison exercise yard. The prisoner can see a little bit more of the sky, but he still has a pretty limited angle of view of that sky. And now here's a suburban street, much bigger range of sky that we can see, but we have 3-story buildings on both sides of the street. So that does limit a little bit of our angle of view, but we got a nice big view of the sky. And then now we have some wide open spaces where you can see almost 180 degrees from horizon to zenith overhead to the next horizon, a wonderful angle of view. So let's put some numbers behind this. So if we were to have a protractor and you were to represent the horizon or the eye level as 0 degrees and then 90 degrees overhead. So you can, if you had wide open skies, you'd be able to see 0 to 90 where 90 is overhead. And then if you took another protractor, a circular protractor, and this one measures 360 degrees, this would represent our azimuth. So you can turn in any direction. You could face north, south, east, or west, or any angle in between, and you could represent with another angular measurement called the azimuth. And so frequently when people are studying the sky, specifically, like the path of the sun in the sky, they use a diagram looking kind of like this. So the ground, the brown ground, it does look like a little flat, patch of earth. But then the sky above that little flat patch of earth, above the observer, is shown to be a hemisphere, an exact half of a sphere. So Penn State has an online course that you could page through. Of course, you won't be able to get college credit, but all the resources are there. And the course is on solar energy. All right, and Professor Brownson has some really interesting diagrams, which I've copied into this slideshow. So here's a picture of what he calls the sky dome. And so Professor Brownson writes, the sky dome refers to the sum of the components for the entire sky from horizon to zenith and in all azimuth directions. And so again, it is represented as a half sphere. okay, a half sphere. So you can look in any direction, you can look at any angle of elevation under this hemisphere. And you can actually graphically represent this using a couple different methods. One is a polar projection, and the other is an orthographic projection. So with the orthographic projection, it's just basically a sheet of graph paper, but the horizontal axis is the azimuth from 0 to 360. So that's kind of like wrapping around you. The vertical axis is the angle of elevation from 0 degrees on the horizon, or the eye level, to 90-degree zenith directly overhead. You can also do this with a polar projection. And this time, the azimuth, it makes a little bit more sense because the azimuth is shown as a circle, 0 to 360. But now the angle of elevation is shown as the radius of this graph, 0 degrees on the horizon to 90-degree zenith. Now, I always emphasize in my videos, I really encourage people to get outside and make careful measurements. And you don't need expensive equipment to do this. So, for example, it's great if you have a theodolite, which may cost hundreds or thousands of dollars. If you have the training to use it, I mean, that's wonderful. Then use a theodolite. But you can actually take some pretty decent measurements. If you're interested in to the nearest couple degrees or so, you could measure the azimuth using what I call the cardinal azimuth tool. It's just a couple of yardsticks attached together with a scale, so you can measure the azimuth of something in your field of view. You can also measure the angle of elevation of something using a clinometer. So that little picture shows a solar clinometer. It's best to find the angle of elevation of the sun. But my point is that you can make tools and you can measure things. You can measure their position in the sky. And again, it's a hemisphere. The sky, the locations of things in the sky is a hemisphere. All right. So Walter Bislands has created a wonderful simulator where, so here he's got the one version of the flat Earth. The flat Earth might not necessarily look like this, but basically he's got the observer. This person is standing in subtropical Africa, and so that person's perspective, the sky is a dome from that person's perspective. Okay, but if the Earth is a globe, you can also take that person. Again, here's that image of Africa from before. But you can actually place him again in sub-Saharan Africa, or I'm sorry, subtropical Africa. And if he looks up at the sky will appear to be a hemisphere. Okay, so it really doesn't matter the shape of the Earth. So again, because we lose depth perception with distance, and the view relies on geometry and not the human eye, any clear skies observer on Earth, whether the Earth is flat or whether it's a globe, will have a hemisphere angle of view. And what do we mean by hemisphere? 360 degrees of azimuth, those are your compass directions, and a 90-degree field of view or angle of view from eye level or the horizon all the way up through zenith directly overhead. So in conclusion, the sky is a dome, no matter the shape of the Earth. So your comments are welcome. Please be respectful and kind to each other. Thank you.